Usually when we think about uh, the footprint of our modern lives, we tend to picture the big things.
Right, the obvious stuff.
Yeah, like the exhaust from cars on the highway or, I don't know, plastic bags blowing across a parking lot.
Smokestacks.
Exactly, smokestacks. It's all very visible. You can just point to it and say, there is the pollution.
It's a footprint we can actually see and smell. It feels immediate.
But then, and this is something everyone listening can relate to, you walk into your own home, you open that one specific drawer in your kitchen.
Oh, the junk drawer.
The junk drawer, or, the bottom drawer of your desk. And you look inside, and it's just filled with tangled charging cables that don't fit anything you own anymore.
3 old smartphones with shattered screens.
Yes. A digital camera from, 2008. Maybe a tablet that takes 30 minutes just to turn on.
And the thing is, it's completely silent. It doesn't look like an oil spill. It just looks like history.
That is exactly it. It's like a personal museum. We upgrade our devices every 2 years. We marvel at the better cameras.
The faster processors.
Right. But where does the old tech actually go? When you finally throw all those old phones to a box and drop them off at a recycling bin, what happens next?
That's the grand illusion, really. We think the life cycle ends the moment it leaves our hands.
Out of sight, out of mind.
Exactly. But that moment is actually just the beginning of a incredibly complex, highly toxic, and quite frankly, globally significant journey.
Okay, so let's unpack this. Because today, we're doing a deep dive into a topic that touches every single person listening. We're going to act as your subject matter experts and sort of your pedagogical coaches to give you the ultimate shortcut to being well-informed on this.
We're pulling from a meticulously researched book called E-Waste, Recycling and Management: Present Scenarios and Environmental Issues.
And our mission today is to break this down in a highly structured, chapter-by-chapter masterclass. We'll give you the big ideas, the deep dives, and actionable takeaways for each section.
Because e-waste isn't just a simple pollution problem, it's a massive economic puzzle and a geopolitical minefield.
It really is. I mean, the sheer scale of global electronic waste is staggering.
Yeah.
So let's jump right into Chapter 2. The focus here is on reconfigurable recycling systems.
Right.
So what is the big idea for this chapter?
The big idea in one sentence is that efficient e-waste recycling requires dynamic, reconfigurable disassembly systems that can actually pivot based on fluctuating waste volumes, labor costs, and material purity.
Okay, so for our advanced deep dive into this, let's imagine that cardboard box of your old phones actually makes it to a facility. What does the factory floor look like? Because the book makes it clear you can't just throw everything into a giant wood chipper.
No, absolutely not. And the reason is the heterogeneity of e-waste. If you run a paper recycling plant, you deal with paper.
Right.
But an e-waste plant, on a Tuesday, they might get 5,000 smartphones, 200 industrial air conditioners, and, 10,000 tangled USB cables.
So you need a very rigorous process.
Oh.
The expert authors outline a 5-step disassembly planning process.
Right. Yes. Step 1 is analyzing environmental requirements. You have to know the legal and ecological baseline for the specific materials on your loading dock.
Because some of them are highly hazardous.
Exactly. Step 2 is waste stream volume. Are you getting 10 tons a day or 100?
Which dictates if you use manual labor or machines.
Right. Then step 3 is the productivity of the plant, calculating the actual throughput without causing a bottleneck. Step 4 is the financial reality costs and revenues.
Because at the end of the day, it's a business.
Always. You balance extraction costs against global market prices. And finally, step 5 is analyzing the physical end-of-life products themselves.
And this is where the deep dive gets really stark, because the physical characteristics vary wildly. The text contrasts cooling appliances with IT equipment.
Right. Take a cooling appliance, like a commercial refrigerator. You can't just smash it.
Because of the gases, right?
Exactly.
Yeah.
The very first thing mandated by international law is the extraction of hazardous refrigerants like CFCs and HFCs.
Those are the ozone-depleting greenhouse gases. So if you just crush it, you release a toxic cloud.
Yeah, completely negating the benefit of recycling the steel. So technicians have to use regulated vacuums to siphon off the gases first.
Wow. But then on the complete opposite end of the spectrum, you have IT equipment, like smartphones.
Right. You aren't dealing with pressurized gas there. You're hunting for precious metals on the printed circuit boards. Gold, silver, palladium.
But getting to a smartphone's motherboard is, it's a nightmare. They use industrial adhesives, the batteries are glued in.
And that's the tension. If you shred the phone automatically, the tiny amounts of gold get lost in the dust.
Yeah, so to get a high purity yield, You need human hands to carefully pry it apart and avoid puncturing the lithium-ion battery.
Which is a massive fire risk.
I have to say, reading this, I kept thinking of an analogy. It's like a commercial kitchen trying to cook 50 different cuisines simultaneously. You have heavy demolition with the refrigerators leaking gas in one corner, and then delicate watchmaking with glued-together smartphones in another. How do they balance that?
Well, that's why the system must be reconfigurable. It's modular. They might have a manual station at the front for the high-value boards, and then route the bulk plastic into automated shredders.
So if the price of gold drops by 50% but recycled copper triples,
They literally reconfigure the layout overnight. They shift labor from the smartphones to speeding up the copper shredding lines.
okay, so let's hit the connective tissue here. Understanding this physical factory floor gives us the baseline of how disassembly happens, which leads us directly into why the economics dictate global policy in Chapter 3.
Exactly.
Let's do a quick practical recap of Chapter 2, 3 actionable takeaways for you listening.
Yeah.
1. Classify and segregate e-waste strictly by material hazard and value.
2. Design processing lines to be reconfigurable based on shifting costs and volumes.
And 3. Prioritize extracting high-value components, like mainboards, to subsidize the cost of processing the toxic stuff.
All right.
Now, here's your critical thinking challenge for this chapter. How do you balance the trade-off between the speed of automated shredding and the high-purity yield of manual disassembly? Keep that in mind.
It's a tough balance.
It really is.
Yeah.
Okay, moving to Chapter 3, an economic assessment of present and future e-waste streams, specifically looking at Japan's experience. What's the big idea here?
The big idea is that e-waste generation correlates positively with a country's GDP. So managing it economically requires integrating recycling directly into the upstream manufacturing supply chain.
Upstream. Okay, so for the advanced deep dive, the text introduces input-output tables, or I/O tables.
Yes, for life cycle policy analysis.
So instead of just looking at the recycling plant's balance sheet, I/O tables map the true comprehensive life cycle costs across the whole economy.
Right, and when you apply that to e-waste, you see a depressing reality about transportation.
The bulky appliance paradox.
Exactly. The I/O tables show that the economic burden of transporting a heavy washing machine, paying the driver, the diesel, the time, often completely outweighs the commercial value of the metals you eventually recycle.
So you might spend $50 moving it and only get $10 of steel out of it.
You're losing money before you even turn on the shredder.
And what blew my mind from the source was the GDP correlation. There's a direct statistical link between a nation's wealth and the e-waste it generates.
It's virtually a law of physics at this point.
Yeah, regardless of their stage of economic development. If GDP goes up, e-waste volume goes up.
And if we connect this to the bigger picture, it's a huge paradox. We want global poverty to decrease, which means GDPs rise, which means more refrigerators and laptops are bought and discarded.
So you can't just recycle your way out of it at the end of the pipe. The math fails.
Which is why the solution is upstream. Products must be fundamentally redesigned by suppliers to minimize waste.
Designed for disassembly. If a tech company uses 50 proprietary screws and industrial glue, they are actively making recycling economically unviable 10 years down the line.
Exactly. The burden has to shift to the engineers designing it today.
Okay, so the connective tissue here. We've moved from the physical factory to macroeconomic policy and supply chains. Now we understand the economic constraints, which sets up the cutting-edge technologies in Chapter 4 that try to overcome these barriers.
Right.
Let's do the practical recap for Chapter 3. 1. Recognize that economic growth intrinsically drives e-waste generation.
2. Utilize input-output tables to map the true life cycle costs of a product.
3. Force collaboration between waste managers and upstream manufacturing supply chains.
That's the only way.
And your critical thinking challenge. If transportation costs make bulky appliances unprofitable to recycle, should policymakers impose a disposal transport tax right at the point of purchase? Something to chew on.
That would definitely change consumer habits.
Totally. Okay, Chapter 4. Recent technologies in electronic waste management. The big idea here is that the exponential growth of global e-waste necessitates advanced, multi-stage recovery technologies to extract value and prevent contamination.
Because the scale's just terrifying.
Yeah, for the deep dive, the tech states we are currently generating around 41 million tons of e-waste globally, and it's increasing by 3 to 5% every year.
It's hard to even conceptualize 41 million tons.
I mean, that's like, what, 4,000 Eiffel Towers?
Yeah.
Made of toxic plastic and precious metals, tossed in the trash every year.
Exactly. So The EPA has a hierarchy to deal with this: reduction, reuse, and recovery.
Reduction being the durable design we just talked about. Reuse is handing down your old phone.
But recovery, that's the heavy industrial science.
Right. The industrial separation strategy has 3 stages. First is sorting and disassembly, which is manual and expensive.
Taking out the batteries and hazards.
Yes. Stage 2 is size reduction, shredding everything down to a uniform 6 to 8 millimeters.
Why that specific size? For stage 3, separation. Magnets pull out the iron, and then they use mechanical separation, like eddy current separators, to launch non-magnetic metals like aluminum and copper into different bins.
But that only gets the bulk metals, right? Not the microscopic traces of gold and rare earths in the microchips.
Right. For those, you have to alter the fundamental chemistry of the waste. You move into pyrometallurgy, specifically a 6-step thermal plasma treatment process.
This part is wild. So steps 1 and 2 are collection and shredding. Step 3 is putting that gravel into a chemical reactor and blasting it with thermal plasma.
We're talking temperatures exceeding 10,000 degrees Celsius.
10,000 degrees.
It vaporizes the plastics and organic materials into a synthetic gas,
Leaving a molten pool of complex metals,
Mhm.
which is step 4, metal separation. They separate the glassy slag from the heavier metal alloys.
And then step 5 is acid leaching, hydrometallurgy. They submerge the alloy in vats of highly corrosive acids, nitric, hydrochloric, to selectively dissolve the metals into a liquid solution.
And finally, step 6, hydro and electrometallurgical operations. They run an electrical current through the acid to pull the pure individual metal ions onto a cathode.
Pure copper on one plate, pure gold on another.
It's basically like trying to unbake a cake to get the original flour, sugar, and eggs back, except, using 10,000 degree plasma and boiling sulfuric acid instead of a whisk.
That's a very accurate, if slightly terrifying, analogy.
But it takes massive amounts of energy. Is it even worth the carbon footprint?
That's highly debated. If powered by coal, maybe not. If powered by renewables, yes. But the capital investment is hundreds of millions of dollars.
Which brings us to the connective tissue. Chapter 4 shows us these ideal high-tech solutions in wealthy nations, but it perfectly highlights the stark contrast with emerging economies, which totally lack these marvels. Which leads right into Chapter 5.
Right.
Magical recap time for Chapter 4. 1. Implement durable designs for the reduction phase. 2. Utilize 3-stage mechanical separation for maximum material purity.
And 3, apply complex treatments like thermal plasma and acid leaching to recover precious metals safely.
And the critical thinking challenge. How do you justify the immense energy costs of a thermal plasma reactor against the environmental benefits of the metals it recovers?
It really is a massive trade-off.
Okay, diving into Chapter 5. Recycling challenges for electronic consumer products from a developing country's perspective. The big idea is that developing nations face a multidimensional web of barriers that actively prevent formal circular economy models.
Yes, it's not just a matter of saying build a plasma reactor.
Right, so for the deep dive, the expert text categorizes these overwhelming barriers into specific buckets.
There are financial and economic barriers. The capital just isn't there. There are environmental, market, legal, and policy barriers.
Because environmental regulations might be totally non-existent.
Exactly. Plus management, knowledge, and technical barriers. If your local power grid fails daily, you cannot run a continuous thermal plasma reactor.
And because of those barriers, here's where it gets really interesting. You get this concept of urban mining versus primitive recycling.
Right. Urban mining sounds great on paper, extracting metals from discarded electronics in cities instead of digging new mines in the earth.
It sounds like a slick green tech startup.
But in developing nations, urban mining is often done by the informal sector. It's not a high-tech facility. It's a family in a backyard melting lead solder off a circuit board over an open fire.
Inhaling toxic fumes just for a few cents of copper? It's tragic. And the text points out that reverse logistics is a massive hurdle here.
Yes. Reverse logistics is the process of moving goods from their final destination, the consumer, back to the producer for value capture or proper disposal.
It's like trying to make a ribbon flow backwards.
Yeah.
Forward logistics is easy because consumer demand pulls the product forward. But reverse logistics fights gravity. No one wants to deal with the broken phone.
Exactly. It requires massive infrastructure and consumer participation, which those 8 barriers completely block.
So the connective tissue here, seeing the ground-level struggles of developing countries, makes it clear we need a comprehensive framework connecting local microscopic actions with global macroscopic policies, which is exactly Chapter 8.
It perfectly bridges the gap.
Let's do the practical recap for Chapter 5. 1. Categorize and systematically dismantle specific barriers, like legal or technical hindering local efforts.
2. Promote formal urban mining over primitive, hazardous extraction methods.
And 3. Integrate reverse logistics directly into the circular economy. And the critical thinking challenge: if you were tasked with formalizing the e-waste sector in a developing country, how would you incentivize unregulated workers to join a formal system?
You'd really have to make the economics work for them.
Definitely. Okay, Chapter 8, E-Waste Management from Macroscopic to Microscopic Scale. The big idea here is that solving the crisis requires a synchronized approach, blending macroscopic government policies with microscopic metallurgical techniques.
Right, it's a 3-level approach.
So for the deep dive, let's look at those levels. First, the macroscopic.
That's government roles and a crucial concept called extended producer responsibility, or EPR.
EPR. This is massive. It means the manufacturer is legally and financially responsible for the entire life cycle of the product, including its ultimate disposal.
Exactly. They can't just sell you a phone and wash their hands of it. It forces them to design for disassembly, because they're the ones paying to tear it apart later.
It puts the externalized cost of pollution right back on their balance sheet.
Brilliant.
Okay, what's the mesoscopic level?
That involves tracking physical reality using material flow analysis and life cycle assessments.
Tracking where the toxins and valuable metals are actually flowing through a region so you can intercept them.
Exactly. And finally, the microscopic level, which is the actual chemical recovery. We talked about pyrometallurgy and hydrometallurgy, but there's also biohydrometallurgy.
Oh, right. This was amazing. Using naturally occurring microorganisms to extract metals.
Literal metal-eating bacteria, like Citothiobacillus ferroxidans. They naturally create a localized acidic environment that oxidizes the solid metals into a water-soluble solution.
It's biomimicry. But it takes weeks or months instead of minutes, right?
Right. It's slow, but it's very clean and uses a fraction of the electricity.
But the text is clear that while these labs exist in wealthy nations, the reality on the ground elsewhere is visceral. Places like Nigeria, Ghana, India, China.
Untrained individuals are burning wires in the open to extract copper.
Burning away the PVC plastic, which releases massive amounts of dioxins into the air, devastating local public health.
And this raises an important question from the source material regarding the consumer's role. The authors explicitly list consumer habits like avoiding addiction to gadgets and extending product shelf life as part of the macro strategy.
Okay, I have to jump in and push back on the authors here. Is it really the consumer's fault they're quote-unquote addicted when massive tech companies intentionally design products with planned obsolescence?
It's a fair point.
I mean, they glue the batteries in so you can't replace a $20 part. They change the charging cables. They throttle old software. It feels deeply unfair to blame the consumer when the system is rigged to force annual upgrades.
That tension is exactly why extended producer responsibility is so crucial at the macro level. It targets the upstream design.
Exactly. So the connective tissue for Chapter 8, we have the tools, from macro policies to microchemistry, to recover materials. But why is recovery so urgent? Because, as Chapter 10 reveals, the Earth is physically running out of these materials.
Right. It's a hard geological limit.
Practical recap for Chapter 8. 1. Enforce extended producer responsibility to hold manufacturers accountable.
2. Apply material flow analysis to track toxins and metals.
And 3. Educate consumers to maximize lifespan, even if we think corporations bear the brunt of the blame.
Right.
And the critical challenge: how can a government effectively ban the open burning of wires when it's the sole source of income for a marginalized community? That is incredibly difficult.
It's a huge socioeconomic hurdle.
Let's move to Chapter 10. E-waste management and the conservation of geochemical scarce resources. The big idea. E-waste recycling is an urgent, existential necessity to reclaim scarce natural resources rapidly depleted by the tech industry.
It's no longer just about pollution control.
Right. The deep dive here highlights the sheer volume. 45 million tons of e-waste generated every year globally, and it's packed with complex metals and polymers.
But the most critical parts are the geochemically scarce elements, rare earth metals.
Right, things like indium for touchscreens, neodymium for vibration motors, cerium for LED colors. Modern tech doesn't exist without them.
And there's a severe scarcity, not just a finite amount in the crust, but they are incredibly difficult and destructive to mine virgin ore for.
And politically fraught, since only a few countries control the active mines.
Exactly. So because extraction is so difficult, a massive, undocumented, illegal flow of e-waste occurs.
It's cheaper to exploit poverty.
Yes. Brokers illegally ship dead laptops, labeled as secondhand goods, to disempowered populations in Southeast Asia or West Africa, where unprotected workers smash them open for the rare earths.
It's like we are burying literal treasure chests in landfills all over the world, only to realize we've emptied the actual physical gold mines to make them. We're throwing away the exact elements we're desperate to find more of.
It's a tragic irony.
So, the connective tissue, the physical depletion of the Earth's resources, perfectly frames our final discussion. The ultimate impact of this massive, toxic industry on human health and our global future, which is chapters 11 and 12.
It all comes down to the human cost.
Practical recap for chapter 10. 1. Target geochemically scarce elements for priority recovery during urban mining.
2. Implement economic incentives to capture materials before they are illegally exported.
And 3. Develop technologies to safely separate complex materials without losing those trace elements.
Right.
And your critical challenge. If a specific rare earth element for smartphones becomes too scarce to mine, how will that shift the geopolitical power of nations that currently host massive e-waste dumps? That's a wild thought.
Suddenly, those dumps become highly strategic reserves.
Exactly. Okay, final chapters. Chapters 11 and 12. Sustainable electronic waste management, environment, and human health. The big idea. Sustainable e-waste management is inextricably linked to achieving the UN's Sustainable Development Goals and preventing a public health crisis.
Yes, the synthesis of everything we've talked about.
For the deep dive, the text shares a shocking stat. From 1992 to 2005, the lifespan of a computer shrank from 4.5 years to just 2 years. We cut it in half.
We doubled the velocity of our waste.
Oh, wait.
And that threatens the UN SDGs, specifically Goal 3, which is good health. Goal 6, clean water. Goal 8, economic growth. Goal 11, sustainable cities. And Goal 12, responsible consumption.
And the text reveals the dark geography of this. 80% of rejected e-waste from developed nations like the US and Europe is exported to developing nations.
The global north is shipping its toxic footprint out of sight.
But by 2030, developing countries are projected to discard 600 million PCs per year domestically, double the 300 million discarded by the developed world.
They are facing a dual crisis, being a dumping ground and accelerating their own domestic waste.
So what does this all mean for you and me? What is the actual biological reality of this?
Well, e-waste contains over 60 metals, including heavy hitters like cadmium, lead, and mercury.
Elements biology has absolutely no defense against.
Right. Unregulated recycling acid baths, crushing monitors, leaches these directly into the soil and the human bloodstream.
Like lead, the body mistakes it for calcium and absorbs it into bones and the brain. In children, it causes irreversible neurological damage.
And cadmium causes irreversible kidney failure. Mercury is a potent neurotoxin that destroys the central nervous system.
It's an active public health catastrophe.
Which is the ultimate connective tissue. The economic, technological, and geographic threads all culminate in the human body.
Final practical recap. 1. Align corporate and national recycling strategies directly with the UN Sustainable Development Goals.
2. Implement strict international tracking to halt the transboundary movement of toxic e-waste.
And 3. Demand the phase-out of highly toxic heavy metals like lead and cadmium in new devices.
Absolutely.
And your final critical challenge. If you know your old laptop might end up in a toxic acid bath overseas, what immediate steps can you take to ensure responsible disposal?
It takes actual research on the consumer's part.
It really does.
Right.
So we've covered the macro policies, the microbacteria, the economics. Thank you all for joining this deep dive. But before we sign off, I want to leave you with a final provocative thought that builds on this, but wasn't explicitly in the text.
Okay, let's hear it.
What if, in the near future, you don't actually own your personal electronics at all?
Wait, really? Like a subscription model for hardware?
Yes. Imagine a world where you strictly lease your phone or laptop. The manufacturer legally retains ownership, and they track it, and they legally reclaim every single microchip, rare earth metal, and plastic casing the exact moment you're done with it.
So it forces a perfectly closed-loop system.
Exactly. Driven by pure corporate self-interest because they need those scarce materials back to build the next leased device. How would that change your relationship with the technology currently in your pocket if you knew you were just borrowing the atoms?
That would completely redefine consumption. We wouldn't be consumers of materials, just users of functions.
Something to mull over. So next time you look at that junk drawer, rethink it. Think of the rare earths, the global supply chains, and the immense human cost. Thank you so much for joining us on this deep dive, and we'll catch you next time.